what is aquaphotonics is, I put a second title which says what it is, and I'll try to lead you and go together with you until I realize that probably we have mutual understanding about why water is a collective mirror and why water is a holistic biomarker. Water and light. Water could be a mirror, and mirror could be a mirror only if we have a light. A light brings the meaning of mirror, right? So water is a mirror on molecular level as well, and it is not two-dimensional mirror, it is a n-dimensional mirror. Jerry started with history. Here's some history since 16th century. And when you read this, at least when I read this, I was wondering how it's possible for Paracelsus in 16th century to realize that water governs the process in the cell and all the processes as a solvent. And the second is very important, I think, and it matches with what I am going to tell you today, with transport of the protons. And they knew that in the 16th century. And again, Albert Szent-Györgyi. But I would like to add to what he said. He said that life is water dancing to the tune of solids. And I would like to add, and the energy fields. Again, I'm going to talk about light being a source of perturbation to the water, which means a source of information that we can extract from the water. And at the same time, using light, we can probe the water. We can perturb, we can add an energy to the water. As Professor Hamarov mentioned, infrared light, which I'm going to talk about, is a source of energy and is a probe also that we can measure water. Just to remind you where we are, aquaphotonics is all about light and water, and light is the electromagnetic field starting from X-ray to microwave. But in between, each particular region obviously has its own meaning when thinking of water. But the good news about the light that I'm going to talk to you, called near-infrared light, which is next to the visible but invisible, it is not like infrared light, which is wholly absorbed by the water. It's partially absorbed. Near-infrared light is partially absorbed by the water, and also it is not that high energy light that could, like UV, that could destroy cells. So you can now understand that I'm leading you to explanation how we use this near-infrared light to measure water in living systems. Because as we heard about consciousness today, and what I can see that this conference made a huge leap towards coherence. And I think we came to this point at the end when many people, not only Emilio, could talk about coherence. And now I will show you two spectra, the spectrum of water and the spectrum of sun. The spectrum of water shows how much energy water absorbs at each wavelength. I mean, each wavelength means different level of energy, but the y-axis shows how much of this energy water really absorbs. And what you can see here is dip, and this dip is here, sorry. is exactly in the region of visible light. And it's easy to understand. Water does not absorb visible light because visible light is reflected by the water. So water is a mirror because of the visible light. When we look at the water, we can see the surroundings. Next to the visible light is this range, which is called near-infrared range. It is, water absorbs a little bit, but not like infrared, so we can still measure. And it has a specific spectral pattern that could be used as a marker. This is the spectrum of the sun, but this is the intensity spectrum, which means that the maximum of the sun intensity is in the visible. Nature is clever, as you could realize. In the visible light, water does not absorb. In the visible light, sun has the highest intensity. So we could see around. The surface of the water is 70% is covered by the surface of Earth by water, and the 70% go everywhere, and as we heard this morning also in the universe, maybe the same percentage. So we want to probe this water and we want to measure it. And the way the way that I'm going to talk about is this near-infrared light, and this is one of the instruments. And these are portable instruments that we have been using in our experiments for non-invasive monitoring. Okay? This is important because it says that with this light, we can take a spectrum which has thousands of wavelengths. You can imagine with a very high resolution, at every particular 0.1 nanometer or 0.001 nanometer, we can take a signal. So we can have thousands of points for one particular sample. And on the top of it, we can monitor the sample, we can acquire this data over the time. So we could have a huge big data, and we can extract information from this data, and which will tell us a lot of things. So this is the spectrum, the near-infrared spectrum of the water. The wavelength range is from 680 nanometers to 2500 nanometers, 2.5 microns. Okay? You see like broad peaks, and if there are chemists among you, maybe they'll say, how can you see something there? Of course you can see it. I mean, we cannot see these sharp peaks in infrared. No, but if we analyze this data with multivariate analysis or so many different methods for data mining and artificial intelligence, etc., we could find really lots of information and specific peaks and specific spectral patterns of the water in living systems, in aqueous samples. So light turns on the mirror, light turns on the water into a molecular mirror. Why is that? Because imagine water, as we all know, water is a network of molecules. And a single, other than water molecule, coming into this network will change it. And we, with this near-infrared light, which is the overtone, I would say, we can use overtone spectroscopy, we can measure this. We can measure all the changes in covalent bonds, speaking with this contemporary way of speaking. So we talk about hydrogen bond, and we talk not coherence yet. Hydrogen bond and covalent bond. Hydrogen bonding network influences covalent bonds. So this influence, we could find it. We can measure with the spectra in the infrared range. So aquaphotonics, what it is like, I'll talk about this yin and yang. It's not the reductionism, it is a complex system approach. So we want, what we are doing at the moment is this omics, proteomics, genomics, metabolomics, 59 at the moment, omics different areas that we measure single molecules. This is the reductionism. The problem is that we cannot connect all the molecules at each point of time to know about the function of the system, because the function is a function of time. So we need this complete system. And aquaphotonics is saying, okay, so we'll look at the water. We use the light that can analyze the water, can probe the water, and every single movement, every single change of a small change of single molecule will influence the water metrics. So we can measure the water metrics, and then we can make models for each possible perturbation, being temperature, humidity, wind, various molecules, etc. Okay? Aquaphotonics describes the stage, not the players on the stage. Okay? If we can see it like yin and yang, I just want to make a connection with the second part of my talk. I think, like Professor Hammer was talking, the body is interesting. And the body is this vacuum, a zero-point field. And maybe we might be able to measure it with infrared spectra. So, because now one step back, how aquaphotonics works. I'll say, so we induce perturbation to the system. We have to change the water metrics. Why? Because entropy means information. The changes will bring knowledge about the system. So and the good news that you could see today at the end of the talk is that we do perturb our sample with light that we use to measure. It's brilliant. You use this light, and it is a perturbation, and it is a probe. So you change your sample, and you measure how it has changed. So, but aquaphotonics has to have a structure. So we have this aquaphoton, which I call aquaphoton, is the database of the water absorbance bands. Everywhere, all the possible absorbance bands that water changes the spectra. So we found out that these bands are, we can learn about those bands by inducing perturbations and analyzing the systems. So in the entire aquaphoton of different systems, in all these overtones in the infrared range, will be our tool to analyze and systems in real time. WAMOX are those water matrix coordinates, means all these absorbent bands. And this is a table that we show that only the first overtone, which is between 1300 nanometer and 1600 nanometer, only the first overtone region, we have found 12 specific water absorbance bands related to different structures of water, like dimer, trimer, tetramer, or dimer with OH on the top, or trimer with OH, with hydroxyl, or protonated dimer, protonated trimer. All of those specific structures have a specific absorbance band. So all these we call coordinates. Imagine we stay at those coordinates and we look at the water and we can see all the changes there. These are the assignments of few of those bands, and you could see what kind of structure we could learn about. Okay? And the aquagram is the way that we can present what is visually. We could see the spectral pattern. As I said, why water spectrum is a holistic marker, because looking at this, you could know your system if this is having more hydrogen bonded system, or it is less hydrogen bonded system, as we use now. We use this way of expression and this way of evaluating the water system, the aqueous systems. Now, this is the spectra of the vapor, and this is the spectra of the water. When you look these two spectra, what do you see? You see that in a sample of the water we have vapor, and also we have ice. So all these structures are in the liquid water, but in different ratios. So we have these bands are our water matrix coordinates, and all these water matrix coordinates are in this aquagram that when we look at, we see that this is the less hydrogen bonded side. We'll talk about these two duality, yin and yang. And this is the hydrogen bonded side. Well, in between is the water. Now, from now on, I will talk about an experiment that we took spectra of samples sent by the group of Denino and Elia, Roberto and Germano. These were samples of naphthalene, of water, after naphthalene was placed in that water, with different pH and different electroconductivity, plus a simple distilled water and molecular water at different temperatures. And this work is in memory of Emilio De Giudice, because the last conversation with Antonella and him was on, we were trying to understand what does it mean to have 100 nanometer of coherent zone. And it took me years to understand. I cannot say exactly that I've understood everything, but I want so much to show you what I could see from the spectra. And this is about self-similarity and fractality, which we discussed with Giuseppe Vitiello as well. And the work has been done in my lab together with Zoltan Kovac from Hungary, and inspired by lots of conversations with Paolo and Tony Bell from Berkeley. And these are two sentences that will lead the whole presentation from now on. And they come from the website of Mei Van Ho, which I really admire, and the late Mei Van Ho, which she was our friend, and she's explained coherence so easily to understand. And she stressed on this too, that when energy is absorbed from the vacuum field, the particles will begin to oscillate between two configurations. So I hope you will see this in the results. And so we have, these are the results, the spectra. So we have, this is the first overtone from 1300 to 1600. This is the water spectrum from 25 degrees to 50 degrees at every 5 degrees. So the blue color is for low temperature, and the red color is for high temperature. So you see that the water makes a blue shift. It changes toward less organized system, molecular system. So this is something that it took me quite a lot of time to find a way to correct the spectrum, because near-infrared region has still physical information, being very close to the visible region, and because the particles that we have in the water, as Elia and his group showed in many recent papers and publications, that we could see water in a big conformations, in the big crystals, kind of. So light, because they're bigger than 1.3, 1.6 micrometers, of course, they will scatter light, and they do scatter light. So in a way, when we have a scatter, the spectra changes the slope. So we can detrend. We can cancel the slope, but the slope also brings information. So I will show you today only the results after cancelling the scatter. In the future, we'll work on this because the scatter itself definitely will tell us about these conformations with different size. It's a bit, no, it's a very busy slide, but you could, probably we can go together with you. These are the 5 temperatures here. This is a log plot following Vitiello's papers about fractality and self-similarity. To prove self-similarity, we need to make a log plot of 2 parameters of a system. And if there is a linear correlation between them, he says there is a coherence. Now what we did, the spectrum, the absorbance, the optical density at each particular wavelength, which makes the spectrum, is a log of the ratio between the light penetrating through the sample versus over the light of the source. So we have the log. Optical density is the log, and this is the log of the temperature. The first slide, the graph is for 1.3 micrometers. So we go with the newest instrument we have, we can go 0.5 nanometers. You can see that this linearity tells about coherence. But it doesn't go at certain point, which I don't see here. It changes. But you see that the correlation coefficient is very low. So we have reduced coherence that changes the slope, and here again. This is with temperature for distilled water. Other results are for Naphion. Sorry about that, I have this, okay. Distilled water, and this is for Naphion. Naphion, with the trend for the first consecutive spectrum, you see that we don't have the same coherence like in water, but we do have a certain correlation coefficient, and it does change. I call these bands turning points because we change the sign of coherence. And now, these are the graphs of correlation coefficient that we saw. This is so beautiful. This is the first measurement, the second measurement, third, fourth. Because we do the same sample, we do 5 consecutive measurements. And what is astonishing, so I'll show you later, these 0 points, turning points, are always the same wavelengths. They do change when we change the water type. Now this is for millicube, but it seems, looks very similar. And now this is for Naphion. Look at this, the first measurement, the second measurement is already inducing changes. And this is what I was telling you about light being a probe and light being a source of perturbation. You can see it so beautifully here. The first time when I introduced aquaphotonics, and it was with this experiment, when I showed that the first, second, and fifth measurements of a sample of water are different. And people couldn't believe. They said, if you're right, I have to get out of my job because the spectrophotometer is not good. But water is like that. And you can see, this is the assignment of all these small bands that are in very good consistency with the results. This is for, one is, for Naphion, we did log of pH and electroconductivity. And again, this is the result of infrared paper. When we calculate the absorbance, these bands of Naphion hydration in infrared, when we calculate the first overtone, which I was talking about and I'm talking about, we have overlapping of the same, absolutely the same frequencies of wavelengths. So, as a conclusion, what we found, this is, blue is the light for water, this is distilled water and molecule water. For this, we have these 0 points, slightly, no, absolutely the same for the water, 1364.5, here is the same, here and here, here and here. Those are the same. For different waters, they are the same. But look at this. This is the minimum, minus R, minus 1, and plus 1. At which band we find it, we have 10 nanometers difference. So we have from minus to plus, we have 10 nanometers. And I think this is very important in order to understand the zero field. So now, looking at Nafion, you can see very similar range. So we have absolutely the same. And this is 100 nanometer. This is about 80, 90, this is a little bit less than. And this is the non-coherent maybe zone. I'm saying maybe, because it's still a lot to work on. But I worked very hard to show you this result that I finished just a month ago. Now, these 0 points are very interesting, is that the assignment, when we go back and see these bands, they are assigned to what they are assigned to these structures. 2 of those structures are Zundel and eigencation. And in this area, we have also protonated water and we have hydronium. So I'll show you very briefly, very fast, summarized bands for molecule. The summarized, the legend is, this is the turning point, the 0 point. No correlation. This is the black, and the very high correlation of 1 is at these bands. Now, for different waters, they are different, slightly different. But for pH and EC, they're mainly opposite, but slightly different. And what is interesting, when you have consecutives, 5 consecutives, the turning point for water is the same band. But when you go to Nafion, the 0 point is going the 5th to the higher energy. Okay, with this I would like to end my presentation and invite you to our International Symposium on Aquaphotonics to be held in Kobe, Japan, from 26 to 29 of November this year. Thank you very much for your attention.
Answer a couple of questions?
Yes.
A couple of questions?
Roumiana, well, I couldn't understand when you deal with nafionated water. So from our experiments, the water right next to the nafion for a few hundred micrometers is easy water, and the water beyond that contains varying levels of protons. So vastly different depending on where you take the water. So I didn't understand in your experiments, which water are you taking?
I'm taking the water that has been, because you have a water which has been, the nafion has been in this water sample, right? So the water is already structured.
Well, not far away from the nafion, so it depends where you get your water. If you get your water from right next to the nafion, then yes, it's structured. If you get your water from farther away, then it's much different.
No, I understood the question, but now I'm not talking about imaging. If we have an imaging, if we have a camera, we have this paper and we have published it with IFA. This spectrum will tell us exactly what is the structure next to the nafion. What I've been doing here is with water which has had nafion in it. No nafion in the sample.
Okay, maybe we speak later because
Yes.
the water, the
Yes,
sample,
yes,
it
yes.
depends what distance from the
Okay,
naphthalene. Yeah.
yes, okay.
Thank you, Roumiana, for a really wonderful and inspiring talk. One of the things that occurs to me is that there may be an answer in your work here to Dr. Emoto's work, in which prayers influence the structure of water, which then is crystallized, and you see the difference. The reason I'm thinking this is because obviously the brain and the heart are, connected, and we have a thought or we have a prayer, and that then emits from our heart. If you have several people standing around some water sample, the amount of energy that water is receiving, from the heart energy of these various people is significant. And then you have the possibility of molecular resonance, because, as you showed in those infrared absorption spectra, there are many different frequencies at which water can be resonated molecularly. So obviously, if the heart field of all these people that are making the same prayer enters that water, there's molecular resonance, then there is the possibility for that resonant property to be stored as memory in the water. And then obviously when you crystallize it, you then see the result of that stored memory. So your talk has inspired me greatly, thank you. And I'm going to be ruminating on these thoughts for quite some time to come.
Thank you very much. Thank you. Appreciate it.
Yes, thank you very much for this very interesting talk. Actually, at WETSUS, we are working at an integrated optical chip that works at very similar wavelength as you do. Of course, it's the third overtone of the OH stretch vibration, and I'm wondering, since we know that this vibration changes depending on the amount of ions and the type of ions in the water, and if you put a piece of naphthalene in the water, it will, of course, act as an ion exchanger, so take up these ions and enhance the proton concentration in the water. So could you comment on that, or is that the reason why it's changed? It's the spectra are changing?
I think what has happened is that water has restructured after having naphthalene in the water for a certain time, and we see this restructuring. And this is very highly correlated with electroconductivity and pH of each sample, which is related to the time that naphthalene has been in the sample. And because we know what each wavelength is showing, we could assign it. We can even know, for example, if there are ions, how much is the trapped water molecules between those ions, which are also protonated, for example. Thank you.
Yeah, really, this is a marvelous talk, and thank you very much.
Thank you.
I live in Japan, but this is the first time to meet you in this country. And so
it's a pleasure, really.
Thanks to the Julian. Yeah, you talked about a very beautiful organization of the pure water and the other one in the naphthalene.
Yes.
Oh, that's okay, but if you take a look more carefully about the presence of the water inside of or close to the naphthalene molecule, then they have two totally different areas.
Yes.
One is a hydrophobic area based to the fluorinated atoms, and the other one is the charges. And so there the water should behave in a totally different way. So your spectrum, what do you reflect, or as a mirror, you say, of these parts?
What I have seen with naphthalene samples, for years I have tried to find a certain wavelength that will be highly correlated to the presence of naphthalene. And I could find wavelengths a spectral pattern, which is a combination of bands. And the ratio of the absorbance at those bands is always different. So the difference between, the answer to your question is, when we have Naphion in the sample, we can see hydration. We can see all the molecules that are in the EZ, and they have specific spectral pattern. When we don't have a Naphion, then we stay only with the late structures of the water caused by the presence of Naphion. And this is definitely different, but this is not this time a point of my presentation. Yes.